Welcome back to Chapter 5 in Openstax Astronomy. This video is going to focus just on Section 5.3 because there's a lot of complex ideas happening in this section, and I want to make sure that we go through it slowly and comfortably. Now, when we think back to the first part of this chapter, we learned about the electromagnetic spectrum and the different types of light that exist, and the fact that Isaac Newton originally had this idea that light was a particle, and eventually we figured out that light acts like a wave and sometimes a particle, and it's got this weird property of existing as separate photons that each carry wave properties. Now, Newton's initial understanding of his particle theory that was originally changed to fit the observations came from shining white light through a prism of glass. Now, when white light goes through a prism, it actually splits up into different colors. This is called refraction, and we'll learn more about that idea in Chapter 6. But all the different wavelengths actually have a slightly different angle that they bend, and so we go from having white light to having a rainbow of colors. And so Newton's idea was that there were red particles and yellow particles and blue particles, and that is kind of what's happening here in the sense that there are red photons and yellow photons and blue photons, but they all have wave properties still. This process of taking a light source and breaking it up into its different types of photons or different wavelengths is the heart of this particular section in the textbook. We're going to focus our upcoming discussion, discussion in this video and in the next video, on two different ways in which stellar spectra are observed. Now, stellar spectra, that first underlined term on our slide here, means that we're taking the spectrum of a star, and the plural of spectrum is spectra, and that means we're looking at a particular star and what wavelengths it's specifically producing in what quantities. Now, if we think about the definition of the electromagnetic spectrum, we were saying let's look at all of the different forms of light and just kind of name what they are and what order they go in. With a stellar spectrum, we care about the fact that the star might be making more infrared light than it does visible light, or it might be making more ultraviolet light than it does visible light. And that comes from looking at what's called a spectral curve, which tells us at each of these different wavelengths how much light is being produced. So that's going to be a big focus of today. And then we'll add to our understanding the fact, both in this video and in the next video, that there are also spectral lines, where if we have a nice smooth curve, there might be dips in that curve where it looks like we've just taken out certain wavelengths. And so spectral lines might be dark against a bright background, or we might be seeing a particular source that only produces certain wavelengths of light, and we'll learn where that comes from and why. So the process of going through these ways of observing the light we receive from stars, the reason it matters so much to us is because we can't visit stars. Most of what we know about stars is based on the light that we receive from them. So these curves here shown on the slide, we're going to build up an understanding that these curves come from the fact that different temperature stars produce light in various quantities and in various ratios. Now, when we think about stars, we can't go visit them, and we are going to learn over the next several weeks, the next several chapters in the textbook, that we know a lot about the temperature of stars, the size of stars, the mass of stars, what the inner structure of these stars looks like, and all of that comes from the light that we receive. So this chapter is really important to being able to understand how astronomy actually knows anything about what's outside of our solar system. All right, so the curves on the previous slide are called blackbody radiation curves. That phrase blackbody radiation may sound vaguely familiar because it was mentioned very briefly in our discussion of how we figured out that light has this wave nature to it. It was one of the two observations that helped us understand that light could not be simply a wave, but had to be this photon that was produced in distinct quantities and in distinct little packets of wave energy. To build up to our understanding of what blackbody radiation is, we kind of have to make sure that we're all on the same page for a couple of key ideas that we may or may not have seen in a previous class. So heat, when we use that term heat, what we're talking about is energy. It's a way of talking about energy that comes from the fact that atoms or molecules in the object that we're thinking about are moving at a certain speed. And heat is just saying there is that energy available because those atoms are moving. Temperature is a way for us to actually make a measurement of the speed of those atoms or molecules. If they're shaking around really, really fast, the temperature is a really big number value. If they're moving really slow, the temperature is a small number value. These atoms have speed because they are in motion, and they're in motion because they contain this heat energy. So these terms are related to each other. Now, imagine the room that you're in. If we cranked up the thermostat so it got really, really hot, those atoms would move faster and faster and faster. If instead we kept turning the temperature down so that the atoms moved slower and slower and slower, eventually, at a point where our human bodies would not be able to handle, so it's just a thought experiment, eventually those atoms and molecules are moving so slowly that they stop moving. They no longer have any heat energy. That happens at a temperature that is defined by the concept absolute zero. So absolute zero by definition is the temperature at which there is no heat energy. Now, in the different temperature scales that exist, that idea of absolute zero has a different number associated with it. So the scale of Fahrenheit is what we use here in the US to describe temperatures. Because most of the common range of temperatures that we experience here on Earth falls between 0 and 100, and it's a useful scale for when we're thinking about how hot or cold it is outside. It's not really used in science because water, a nice benchmark for us to make measurements with, freezes and boils at these random temperatures, 32 degrees to freeze, 212 degrees to boil. Numbers that we may have in our mind, at least the freezing point, living here in Michigan, but not something that is kind of a good scientific scale. And that's where the Celsius scale comes in. It's what most of the world uses for their temperatures that they think about in everyday life, but it's defined by how water changes from solid to liquid and liquid to gas. So water freezes at 0 degrees Celsius by definition of that scale, and it boils at 100 degrees Celsius by definition of that scale. So there's 100 Celsius degrees in between boiling and freezing. The Kelvin scale is also used in science, and 1 Kelvin of change is the same thing as 1 Celsius of change. But that whole scale is set to deal with absolute zero properly. So the temperature of absolute zero is defined to be 0 Kelvin. When we figure out what that is in Celsius, it's negative 273 degrees Celsius. And so that's why that Celsius and Kelvin scale differs by 273. Water freezes at 273 Kelvin, it boils at 373 Kelvin. For those curious among you, absolute zero in the Fahrenheit scale is negative 460 degrees Fahrenheit. Extremely, extremely cold. So cold that we don't see those kinds of temperatures in the universe or on Earth. Astronomers use the Kelvin scale. We're going to see that over and over, and so this is our slide to be able to reference back if we forget what it means. And the temperature is, just like any other scale, a measurement of the motion of particles. In our study of the universe, we'll see temperatures that range from about 3 Kelvin, so 3 tiny steps above absolute zero. That's what the space in between stars, that's the temperature of it. Those atoms that exist there are barely moving. And when we get to our discussion of the very start of the universe, we'll learn that in the very first fraction of a second, the temperature of the entire universe was like 10 to the 14 Kelvin. That means 100 trillion Kelvin. All right, now, what really matters to us, now that we've made sure we kind of understand some of these terms, is that any object that is warmer or hotter than absolute zero has atoms moving around. Right now, the atoms that make up our bodies are moving around and hitting each other, and they're producing heat. We feel warm, right? If we take our temperature, we're warm. And that comes from the fact that we're above absolute zero, and it means that we actually produce electromagnetic radiation. Human beings produce infrared radiation. We show up on infrared cameras. We can turn on sinks with our warm hands with that infrared sensor. And if we make an object hot enough, then the electromagnetic radiation it's producing will shift to shorter and shorter wavelengths, so that rather than producing warmth, like we do as human beings, we could have something that is actually physically glowing in the visible, because it's doing the same thing we are, but at shorter wavelengths, at higher energy temperatures. If we imagine heating a piece of iron in a fire, or if we have a metal burner on our stove, when we first turn it on, it doesn't glow, but it's still hot. Don't touch it. But eventually, as it gets warmer, it is a dull reddish glow, and the burners on our stoves won't make it to white hot, but a fire poker could, the very tip of it, where it's shifting to shorter and shorter wavelengths and changing the color that it appears. That's what stars are doing as well. This is what we mean by blackbody radiation. It's that glow that comes from the atoms moving around and hitting each other and producing light, producing photons. So, blackbody radiation, that idea, is just electromagnetic radiation. That previous video that we watched, electromagnetic radiation, is just the movement of light energy from one place to another. And sometimes it's in the visible region, and so we can see it. And so stars are producing blackbody radiation. They are hot, dense objects, and so they produce this. Now, there's a couple of key things about blackbody radiation. The radiation has a particular single wavelength where there's the most of that wavelength produced. That's often called the peak wavelength, and that is based only on the temperature of the object. The peak wavelength is based only on the temperature of the object. In our textbook, there's an equation called Wien's law, W-I-E-N, Wien's law, that relates those two quantities. We don't have to do calculations with it, but we do want to make sure we understand that the peak wavelength depends on the temperature, and only the temperature. The shape of these curves is always going to have the same shape. It's a very complex set of equations that define that shape that we're not even going to talk about. We just want to recognize that it's going to have this kind of up and down shape that's specific, but we won't worry about those specifics. And then the total amount of energy is also based on the temperature. The curve will have a peak, but it will also be a big curve high up or a small curve low down. The peak location is based on temperature, and the up and down is based on temperature and size. So, the total emitted energy is based on the area under the curve. That's an idea, a mathematical idea or a calculus idea, and we don't worry about that part. But the key is that the curves are higher if it's a hotter object. And if we look at this slide a little bit clearer, there are some purple dots indicating the location of the peak wavelength, and that also shifts to shorter and shorter wavelengths as we go to hotter and hotter objects. It may be worth, in your notes, carefully drawing this set of curves and making sure to pay attention to where the peak is and the fact that these curves do not cross each other. They kind of are nesting underneath each other. If a star has a really high temperature, that curve is going to be peaked at a really short wavelength, high energy form of light, and it's going to produce more blue light than it will red, and so that star will look blue. If a star has a temperature around 6,000 Kelvin, like our sun will learn, it's going to produce roughly equal amounts of red and blue, and so it's going to end up looking mostly yellow or yellow-white or even white. And if a star has a really low temperature, it's going to make more red light than it makes blue. And so it's going to look overall red in color. This slide has a set of those ideas where it's showing us where that peak wavelength is using that symbol lambda that we learned in the previous lecture video. And it's something that we're going to work with today to really make sure that we understand the basics behind these blackbody curves. So, thinking about what we've talked about so far, we've got a pause and think multiple choice question for us. So we've got a lump of lead heated to a very high temperature, and another lump of lead that's twice as big that's heated to a lower temperature. Which lump of material is going to appear bluer? So pause and think about this. Okay. Now, when we think about what looks red or blue or in between white, the color of objects is based entirely on temperature. So hotter objects look bluer and colder objects look redder. So the hotter lump appears bluer here. Option 2 is correct. Now, this is going to be the right time to try the lecture tutorial, blackbody radiation. If you've been taking this class online, and sometimes you might pause the video to work on the lecture tutorial, there's one more slide I want to talk about before you try it. If you're taking this class on campus flipped, then we'll be talking through this lecture tutorial quite a bit, and you can pay attention to the tips that I give if you want to, or you can just kind of prepare to be doing that in class. This is going to be the first set of pictures that you'll see on the first page, page 59. But when we get to the next set of figures, there's a couple of key things I want to make sure that we think about or are aware of so that we don't lose too much time spinning our wheels with this lecture tutorial. The far left picture here is the first one that's asked about. There are several questions asking about figure A specifically, and which star looks bluer, which star produces more blue light, which one looks redder, produces more red light, those kinds of questions. Then we shift over and ask about B and eventually set C here. Now, one thing I need to point out, normally I do this on a chalkboard and on-campus classes I still will, is if we look at the previous slides, let me go back in time a bit. We saw these curves kind of nesting underneath each other. This particular slide is showing intensity of light. Whereas in the lecture tutorial, what we're about to do, we're going to be looking at total amount of energy. That total amount of energy cares about the temperature of the star and the size of the star. We can take any of these curves shown on our lecture slide, and if we take that temperature star, but make that star bigger, the curve just goes up instead of left or right, because the peak is based on the temperature of the star. To shift the peak left or right, we have to make the star hotter or colder. And this set of curves is as if we're comparing stars of equal size. So when we get to this third set of stars, comparing star D and star E, what we're going to find is that the peak wavelengths are different, they're different temperatures, and yet the curves are able to be just as high as one another. So the hotter star is normally producing more light, but the colder star is going to have to be bigger in order to compensate and basically be just as big a curve. So keep that in mind as you're working on this particular lecture tutorial. It is a tough one, but it's a really important one for us to build our critical thinking skills and confront a lot of misconceptions or difficult paths of thinking about this topic. Either after you finish the lecture tutorial or as a kind of pre-check, if you haven't yet, another pause and think question for us. Let's say that the sun is the same size as star E and star F shown on our slide here, but it's 6,000 degrees Kelvin. So star F is only 4,000, star E is over 8,000 Kelvin. What wavelength, or what would be true about the wavelength where the sun peaks? So pause the video and think about it. All right, since the temperature is directly in between stars E and F, the peak wavelength will be directly in between stars E and F. The peak wavelength is based only on the temperature. Now, the really important thing that we have to add to our understanding is that all of those curves we've seen up until this point in the video have been really smooth, nice curves. The problem is real stars don't produce nice, smooth curves. Instead, the cores of those stars produce nice, smooth curves. But as that light moves through the outer layers of the stars themselves, some of those wavelengths are taken out of the spectrum. And the next video that we have for Chapter 5 will go into the details of that process. But we're now going to start to think briefly about spectral lines, which we had alluded to earlier in the set of slides, and now is our chance to think a little bit more about those spectral lines. Now, a blackbody curve produces what's called a continuous spectrum. If we took out the information about the sort of up and down part of the curve, and we're just trying to look at what light is produced, a blackbody curve, a smooth curve like that, produces all of the different colors, from long, long wavelengths of red to short, short wavelengths of blue and purple. But that's only one of 3 different types of spectra. We see here that we can have an emission spectrum. All light sources emit light, but an emission spectrum means specifically that we are only receiving certain wavelengths and we're not getting a smooth curve. And an absorption spectrum is one that would look like a smooth curve, and yet it has pieces missing. And so when we're looking at the spectral curve, kind of rectangular box way of considering stellar spectra, we get almost the full rainbow, but there are specific wavelengths that appear to be missing. Now, think about these 3 spectra types: continuous, emission, absorption. It may be useful to draw them into your notes. And now look at the spectrum on our slide here that is the spectrum of the sun as we observe it. So which of the following best fits the sun's spectrum that we receive? So pause and think. All right. Now, the first part of this video was talking about how the sun is a hot object, so it emits a blackbody curve, but we clearly see pieces missing here. There are dark lines and bands missing through this whole thing. The way that we should read this spectrum is it's basically a really, really long rainbow that we're reading like a book. We're just kind of reading line by line all of those different colors. Eventually goes from short wavelengths of blue to long wavelengths of red. We're seeing here a dark line absorption spectrum where we have a nice rainbow with dark lines also there. So this is when we really want to try the lecture tutorial types of spectra. If we look at this curve or this figure here, a hot dense energy source, like we introduced when we talked about blackbody radiation, will produce a continuous spectrum. If we have a hot low density cloud, that low density cloud doesn't make a blackbody spectrum, a blackbody curve. Instead, it only produces specific wavelengths. And in the next lecture video, the next section of the chapter, we'll talk more about why that is. And then if we have a light source, a hot dense energy source, like the filament of a light bulb, that's producing all of the forms of light that then passes through a cooler low density cloud, that cloud will actually steal specific wavelengths and will end up with an absorption spectrum. So try the lecture tutorial types of spectra so that we can really hit home, or if this is if you're taking this course as a flipped classroom, we'll do this one the next time that we meet. But this will really help discuss a little bit more about not just the curves that we've already been working with, but the spectral lines idea as well. All right, after doing the lecture tutorial or simply after thinking through that previous picture, if we were to analyze the light from a low density object, like a cloud of interstellar gas, and we'll learn eventually those are called nebulae, what type of spectrum would we expect to see from that object? So pause the video and think about it. All right, that best matches a hot low density cloud, which would produce a bright line emission spectrum, option 2 here. Now, what's really important for us to kind of get across before we end this video is if we look back at this picture, and this is a real set of data of our sun. On the top, we have the spectral curve, and on the bottom, we have the spectral line information. If I only showed you the spectral line information on the bottom, would we be able to tell the location of the peak wavelength just from that graph part on the bottom with the colors and the dark lines? So think about that briefly. And what we realize is that that alone will not get us the peak wavelength. If we go back, for example, to this slide here, this information does not tell us the peak wavelength or the color or the temperature, because those are all the similar information, of the sun. We need that curve and that peak wavelength of the curve to be able to tell the temperature, and we can't get that peak wavelength information from the spectral line rectangle. So in this video, we've talked about the fact that stars produce blackbody radiation in their cores, but as the light travels through the outer layers of the star, it goes from being a continuous spectrum in the middle of the star to an absorption spectrum by the time it actually leaves the star and then makes it to our telescopes. Spectral curves tell us about a star's temperature, and the spectral lines tell us a little bit about what that star is made of, and that's what we're going to focus on in our next video. So we're going to end this particular video here because there's already plenty of information, and it may be something that you read back through the slides. This particular set of slides is very wordy, so that it's easier to go back and reference some key information. But those lecture tutorials are really meant to help us work through all of this content in a guided kind of way. So I'll see you at the next video.